Physical properties of group 16 elements. Observe the variation in atomic or ionic radii. It increases down the group. Due to increase in the number of shells, atomic and ionic radii increases from top to bottom in the group. The size of oxygen atom is, however, exceptionally small. Now observe the variation in ionization enthalpy. It decreases down the group. It decreases due to increase in size, and the elements of this group have lower ionization enthalpy values compared to those of group 15 in the corresponding periods. Now observe the variation in electron gain enthalpy. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. However, from sulfur onwards, the value again becomes less negative up to polonium. Now observe the variation in electronegativity. It decreases down the group. Next to fluorine, oxygen has the highest electronegativity value amongst the elements. Within the group, electronegativity decreases with an increase in atomic number. Now observe the variation in physical properties, that is, metallic and non-metallic character. It increases down the group. All group 16 elements exhibit allotropy. The melting and boiling points increase with an increase in atomic number down the group. The large difference between the melting and boiling point of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecule, that is O2, whereas sulfur exists as polyatomic molecule, that is S8. Dioxygen. Preparation of dioxygen. Dioxygen can be obtained in the laboratory by heating oxygen containing salts such as chlorates, nitrates, and permanganates. For example, the reaction 2K plus ClO3 minus on heating in presence of MnO2 gives 2KCl plus 3O2. Hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. 2H2O2 gives 2H2O plus O2. Industrial preparation of dioxygen. Take a red lead in a flask. Now heat it slightly. Now we will find a colorless gas evolving from it called dioxygen. The reaction taking place is 2Pb3O4 gives 6PbO plus O2. Text. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapor, and then the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen. Properties of dioxygen. It is colorless and odorless gas. Its solubility in water is to the extent of 3.08 centimeter cube in 100 centimeter cube. Water at 293 Kelvin, which is just sufficient for the vital support of marine and aquatic life. Oxygen has three stable isotopes, that is 16O, 17O, and 18O. O2 is unique in being paramagnetic in spite of having even number of electrons. It is due to the configuration sigma 1s square, sigma star 1s square, sigma 2s square, sigma star 2s square, sigma 2pz square, pi 2px square equivalent to pi 2py square, pi star 2px1 equivalent to pi star 2py1. Combination with other elements is often strongly exothermic. Consider the reaction 4Al plus 3O2 gives 2Al2O3, which is highly exothermic. Bond dissociation enthalpy of oxygen-oxygen double bond is high, that is 493.4 kJ per mole. The type of oxides of oxygen is simple and mixed. Simple is further divided into acidic oxide, basic oxide, amphoteric oxide, and neutral oxide. Acidic oxide. An oxide that combines with water to give an acid is termed as acidic oxide. For example, SO2, Cl2O7, CO2, and N2O5. Consider the reaction SO2 plus H2O gives H2SO3. Basic oxide. The oxide which give a base with water are known as basic oxides. For example, Na2O, CaO, and BaO. Consider the reaction CaO plus H2O gives CaOH whole twice. Basic oxide. The oxide which give a base with water are known as basic oxides. For example, Na2O, CaO, and BaO. Consider the reaction CaO plus H2O gives CaOH whole twice. amphoteric oxide. They show characteristics of both acidic as well as basic oxides. Such oxides are known as amphoteric oxide. Consider the reaction Al2O3 plus 6HCl plus 9H2O gives 2Al H2O whole 6 whole plus 3 plus 6Cl minus, and also the reaction Al2O3 plus 6NaOH plus 3H2O gives 2Na3Al OH whole 6. Neutral oxides. There are some oxides which are neither acidic nor basic. Such oxides are known as neutral oxides. Example of neutral oxides are CO, NO, and N2O. Preparation of ozone. Initially, oxygen is present in discharge tube. Observe that on passing the electric discharge, ozone is formed. A slow dry stream of oxygen is passed through a silent electrical discharge. Conversion of oxygen to ozone, that is 10%, occurs. The product is known as ozonized oxygen. The reaction taking place is 3O2 gives 2O3. The delta H of the reaction at 298 Kelvin is plus 142 kilojoule mole inverse. Properties of ozone. Structure of ozone. The structure of ozone is given here. The reaction taking place is O3 gives O2 plus O. Let us take an example. For example, PbS plus 4O3 gives PbSO4 plus 4O2. Quantitative estimation of ozone. Ozone is dissolved in a solution containing iodide ions. Consider the reaction 2I minus plus H2O plus O3 gives 2OH minus plus I2 plus O2. Iodine liberated is titrated against a standard solution of sodium thiosulfate. O3 is highly explosive, that is, more unstable than oxygen because of the reaction 2O3 gives 3O2. Sulfur allotropic forms. Sulfur has many allotropes, of which most important are alpha sulfur, that is rhombic sulfur, and beta sulfur, that is monoclinic sulfur. Alpha sulfur can exist in two forms, puckered shape and chair shape. Beta sulfur can be prepared by heating alpha sulfur at temperature greater than 369 Kelvin. 369 Kelvin is transition temperature, as you can go from one allotropic form to another allotropic form. Alpha sulfur is yellow in color, while beta sulfur is colorless. The melting point of alpha sulfur is 385.8 Kelvin and that of beta sulfur is 393 Kelvin. The specific gravity of alpha sulfur is 2.06. and that of beta sulfur is 1.96. Alpha sulfur is insoluble in water but soluble in CS2. Text: acid on heating greater than temperature 1000 Kelvin gives S2, which is paramagnetic in nature. Oxo acids of sulfur. Sulfur forms a number of oxo acids such as H2SO3, H2S2O3, H2S2O4, H2S2O5, and H2S2O6, and H2SO4, H2S2O7, H2SO5, H2S2O8. Some of these acids are unstable and cannot be isolated. They are known in aqueous solution or in the form of their salt. Structure of some important oxo acids are given below. Chemical properties, oxidation states, and trend in chemical reactivity. The elements of group 16 exhibit a number of oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2, except in the case of OF2, where its oxidation state is +2. Other elements of the group exhibit +2, +4, +6 oxidation states, but +4 and +6 are more common. The stability of +6 oxidation state decreases down the group and stability of +4 oxidation state increases due to inert pair effect. Bonding in +4 and +6 oxidation states are primarily covalent. Anomalous behavior of oxygen. One typical example of effects of small size and high electronegativity is the presence of strong hydrogen bonding in H2O, which is not found in H2S. The absence of d orbital in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, in case of other elements of the group, the valence shells can be expanded and covalence exceeds 4. Reactivity with hydrogen. All the elements of group 16 form hydrides of the type H2E, where E can be sulfur, selenium, tellurium, and polonium. Some properties of hydrides are given in table. The increase in acidic character and decrease in thermal stability of hydrides can be explained in terms of hydrogen in bond He, that is dissociation enthalpy down the group. All the hydrides except water possess reducing property, and this character increases from H2S to H2Te. Reactivity with oxygen. All these elements form oxides of the EO2 and EO3 types, where E can be sulfur, selenium, tellurium, or polonium. Ozone, that is O3, and sulfur dioxide, that is SO2, are gases, while selenium dioxide, that is SeO2, is solid. Reducing property of dioxide decreases from SO2 to TeO2. Besides EO2 type, sulfur, selenium, and tellurium also form EO3 type oxides. For example, SO3, SeO3, TeO3. Both types of oxides are acidic in nature. Reactivity towards the halogens. Elements of group 16 form a large number of halides of the type EX6, EX4, and EX2. The stability of the halides decreases in the order F- greater than Cl- greater than Br- greater than I-. Amongst hexahalides, hexafluorides are the only stable halides. All hexafluorides are gaseous in nature. Amongst tetrafluorides, SF4 is a gas, SeF4 is a liquid, and TeF4 is a solid.